discussing inductive reasoning. Okay? Now, if I wanted to give you a definition of inductive reasoning, we're going to write down that it's reasoning that is based on patterns you observe. Bless you. All right, so I want you to take a moment to look around the room. I quickly get the attendance in here. Take a look around the room, probably because I have 10 million calendars in my room.
Well, not only that, you have those other papers stacked.
Oh, my papers are stacked. That's true. Okay. What else? Teacher, optimistic, motivational, organized. Nothing else? You walk in this room, you're thinking, this teacher has no personality, just look at this room. Just a normal classroom. Yeah, that is. It is. All right. Okay, so what are you doing right now? You are looking at observations. You're pulling from previous knowledge of what you think of things, and you might possibly looking for patterns. Okay, so you're you're using inductive reasoning to come up with a conclusion. All right, so let's look at an actual number pattern to see if you can use inductive reasoning to come up with the next number in the pattern. So here we have 3, 6, 12, 24. What's the pattern? What's happening from 3 to 6 to 12 to 24? It's all being doubled or multiplied by 2, however you want to think about it. Okay, so find the pattern. So our pattern is, you can either write doubled or multiplied by 2. So there's our pattern. What would be the next two terms? 24 would go to 48. 48 would go to 96. Good. Okay. So there's an example of a number pattern. Now let's look at an actual figure pattern. Can we sketch the next figure in the pattern? What's happening each time? So here I have 2 parts. Here I have 4 parts. Here I have 6 parts. So the next one would have to have 8 parts. Okay, so let's see if we can do this. So 1 across. There we got 4. Now I have 6, 8. Can I do 10? It might be a little bit harder. What it would look like with 10. So 1. Now we're at 4. That is not in the middle. Let's try that again. There we go. 6, 8. What do I need? Another one? Maybe right here. Now do I have 10 slices? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah? Okay. All right. So looking at patterns, trying to figure out what the next thing is going to be in the pattern. Now, the next terminology you're going to be seeing often in this section is the word conjecture. Okay, and a conjecture is a conclusion that is reached using inductive reasoning. So you might be asked to make a conjecture. All it's asking is for you to take a very educated guess on what you think the resulting thing is going to be. Okay? So if you see the word conjecture, it's asking you to make a conclusion about something. Okay? All right. So we are going to make a conjecture about the sum of the first 30 odd numbers. Well, what are my odd numbers? 1, 5, 3, 5, right? So let's look for a pattern. Because what we could do is we could sit here, we could do 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13, and we could do it all the way for 30 digits, which would be a lot. Or we can look for a pattern to see if we can come up with a conjecture or conclusion about what's going to happen. So let's do the first two odd numbers. What's 1 plus 3? 4. Now let's do the first 3. 1 plus 3 plus 5. That gets us to 9. Let's do the first 4. 1 plus 3 plus 5 plus 7. 16. Good. Okay, stop me when you think you've got a conjecture. Let's do the first 5. 1 plus 3 plus 5 plus 7 plus 9. Does anybody see a pattern yet? They all are turning out to be perfect squares, right? Okay. Well, now how do we get from the sum of the first 2 to 4? And the sum of the first 3 to 9? And the sum of the first 4 to 16? Brett?
I see 2 times 2, 3 times 3, 4 times 4.
Which is the same as squaring something, right? So 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Do we need to do another set to prove ourselves that we're right with our conjecture? Why not? Let's try it. If I do the sum of the first 6, so 1 plus 3 plus 5 plus 7 plus 9, need one more, plus 11, that gets me to what? 36. Does that work out? 6 squared? So, instead of adding the first 30 odd numbers, what do we think the sum of the first 30 is going to be? It's going to be 30 squared, right? Because this is equal to 2 squared. This is equal to 3 squared. This is equal to 4 squared. This is equal to 5 squared. This is equal to 6 squared. So the first 30 would be equal to 30 squared, which is 30 times 30? 900. Okay. So the sum, ladies, of the first 30 would be 900. If you don't believe me, you can sit there on your calculator and do it all the way for the first 30 digits. Okay? Conjecture. Got that? All right, let's flip on to the back side of our notes. Next thing we're going to talk about is a counterexample. A counterexample is an example that shows a conjecture is incorrect. I'm sure you guys have heard of counterexamples before. Okay, so we're showing that a conjecture is incorrect. For a counterexample, you just need only one example to prove that something is incorrect. Okay, so if we look at the first example that we need to come up with a counterexample for, it says the square of any number is greater than the original. All right, so the square of any number. I'm just going to pick someone give me a random number. 6. All right, so if I square 6, what is 6 squared? 36. Is the square of any number greater than the original number? Is 36 greater than 6? Yes. Okay, so that's not a counterexample. So now I got to come up with a new number. So that one didn't work. That when I square it, the number is going to be greater than the original. All right, well, in my brain I'm thinking, well, let's try negative. What if I do negative 2 and square that? What's the square of negative 2? 4. Is 4 greater than the original number? Yep, so that didn't work. Okay, so we covered our negatives. There is something out there. A decimal or fraction, same thing. Someone give me let's do a fraction because that's easier.
1
1/4. Okay, so let's do 1/4. Erase this. If you square 1/4, what do you get? What's 1/4 times 1/4? Try again. 1/4 times 1/4. Remember, you multiply straight across the top, straight across the bottom. So it'd be 1/16, right? Is 1/16 larger than the original number? No, it's actually smaller. So there's going to be a counterexample. And you don't have to write anything in sentences. You can just use that as your example right there. So 1/4 is not smaller than 1/16. Put a little slash through that less than sign. So there would be a counterexample. Okay. All right, let's go to part B. You can connect any 3 points to form a triangle. Can you make 3 points so that when you connect them, they don't form a triangle? What would that look like?
Just one.
Straight line, good. So 1, 2, 3. If I connect those 3 points, they do not make a triangle. They make a straight line, which is not a triangle. And then the last one, any number and its absolute value are opposites. What does the word opposite mean? Like, what's the opposite of a positive? Negative. What's the opposite of a negative? Positive. So if I take the absolute value of any number, it always ends up being what? Positive, right? So it says any number and its absolute value are opposites. Well, what if you take the absolute value of a positive number? Doesn't it end up being positive? Are those opposite, 3 and 3? No. So that would be a counterexample. Okay? All right, so I'm going to have